We hope that the students who are here today in high school are being inspired to go into science in the future. We would prefer physics, but it doesn't need to be physics. The physics is really cool. So you see, see if we can get rid of that. So you see all these kiddos, they're in their 70s clothing. I think you guys still wear stuff like this now, right? This is what the youngins do these days? Yep, I see them. But the idea is they're in the same position that you were, or that you are. So we want you guys to really get in here, understand what's going on, ask a bunch of questions, learn as much as you can. I think this is as close as you can get to professional physics without being a student in college somewhere. I mean, unless you want to come do research with us. We'll talk about that later. Why is this still here? I got to get this. Oh, it's not there. Okay. This is what our schedule looks like. We'll have talks on relativity, quantum mechanics, standard model. You guys will learn all about particle physics at the cutting edge. Fermilab is the sister laboratory to CERN. Is one of the world's foremost, research institutions on particle physics. This is a world-class lab here. I don't know if you guys picked that up. We're also going to have talks on how we make and detect particles, quantum computing. We're going to have somebody come talk about neutrinos. That's what I work on. I also have a storied past, well, not storied, but a long history in energy and climate change. I'll be giving that talk. Then we're going to talk about cosmology and some of our other projects. And then it's supposed to be a surprise, but if you paid attention, you'll see that the director will come and talk to you a bit about some of the stuff we do here. Let's go over some norms. This is our first time that we've been in person for an official series in 3 or 4 years. COVID happened in 2019. We closed everything off, added a bunch of new security. Now we're back. So we're testing this out. We have some bugs to work out of this whole process, so please excuse our work. We're keeping the Zoom component, so it's a hybrid format. I hope you guys on Zoom are appreciative. We're going to make sure we pay attention to you. How the speaker wants to run the stage is up to them. So they'll set their own norms. They'll let you know before they talk. And guidelines for you guys is that we're going to treat you like college students. You know, some of you are in high school, but if you're here, we expect you to be mature. That means, you know, don't interrupt the speaker. Don't be rude to the speaker. Understand that we're spending a lot of time with you guys, and this is our free time because we like to do it. On Zoom, I forgot to put this on the slides. We're going to have pigeonholes for you guys to ask questions. We're also going to have chat. So try to get the questions in there. And also, we're here because we want to satisfy your curiosity and spark your interest. Ask as many questions as you have. No question is stupid. Okay? Here's our daily schedule. We have special satellite programs that we're working on. We'll have one next week. But so unless we're in that schedule, we'll typically show up here. We'll also be on Zoom. You'll get a link. And between 8:30 and 9, everyone should arrive. The lecture will begin. We're running a little bit late because I need to tell you guys what the ground rules are. Then we'll have the lecture from 9 to 10, the 5 to 10 minute break at 10. And at 10:50, we should start wrapping up. Things should be over by around 11:10, 11:20. And then you'll go on your tours. The Zoom people will have a virtual component, and the in-person people will be able to, we'll send you all over the lab. So there is a real incentive to come to the lab because you'll get to see things. I mean, this is a It's a multi-million-dollar lab. I think we just hit $1 billion this year. We got a lot of cool stuff. After the tours, you're going to go home. We don't want to see you anymore. I'm joking. We want to see you.
I'm just going to add to what Brian was just saying by saying that this is, it's a public government-funded lab, and we feel that the work that we do belongs to the people. So we feel like it's really important for us to be able to show you guys around because you guys are kind of paying for what's going on, and you're also the future of what we're doing. So we feel like it's really special that we get to do what we do, and we can't wait to share it with you. So we're really happy to show you around.
Okay, so there are rules on attendance. Um, Attendance will be taken in person on Zoom when the lecture starts, and also if you're in person, then you'll sign in when you get here. Um, if you want to get a certificate of attendance, you need to be here at least 8 out of the 11 lectures. I assume you'll be here for graduation, so really it's 8 out of 10. And if you want a perfect attendance award, you need to be here for all 10. There are absences, but we're very strict with them. I think we only give them for SAT and ACT and Science Olympiad. There are certain cases where we can excuse stuff, but we're fairly strict. So ask, but don't expect to get one. All right. Now, before we get started, we need to introduce the people who are running the program. Natalie is unfortunately up there making sure you guys can get in. Nate, why don't you come up? Cindy. So we are currently your co-chairs. I'm actually transitioning out. So you guys, I don't know if this is relevant for you guys because you probably won't be here next semester, but I'm on my way out. I've been doing this for 4 or 5 years. I want to make sure new blood comes in. Again, I'm Brian Ramson. This is Nate Saffold, D. Joe. We're all professional physicists. So, you guys want to say anything?
I guess I'll say that I've been involved with, I don't even know how many years I've been involved with.
You've been here longer than me.
Yeah, longer than Brian, but not a director not a co-director until this year. I've been a lecturer for many, many years. So I'll be giving one of the lectures later in the season. But I'm really excited to be a part of making this happen because, as Brian said earlier, it's a program that means a lot to Fermilab. It was started again by one of our former directors and a Nobel Prize winning physicist, and it was kind of his baby. And so when Saturday Morning Physics has existed for a long time at the lab, and I feel really excited to be a part of it and part of shaping the future of Saturday Morning Physics. Brian and I have a lot of ideas about where to take this. We want to make it more accessible to you guys. We want to make it more diverse, more engaging, and just try to, we do physics, but we're also really interested in education and engaging with the youth and engaging with the public. So we have a lot of ideas. I also want to say, please, this is a collaborative process, right? So we have speakers up here, but they're all just doing the best they can. We have, you guys as students do at least half the work, if not more. So we want to make that possible for you. So ask questions, show up, reach out to us, be a part of what we're doing.
Yeah, I'm Nate. Happy to be here. Yeah, I'm relatively new. Well, I started helping out, I think, last year or a year and a half ago. But it's been a really rewarding experience, even over Zoom. But really, last year, the first time we came in and getting to talk with students was really fun for me. Day to day work in physics. Sometimes it's hard to see the forest for the trees or whatever. But it's nice, get to interact with people that have a lot of enthusiasm for the subject. So yeah, I'm excited. Just if you just want to chat about anything, career stuff, I'll be hanging out afterwards for a little bit. But excited to learn with you all, and yeah, feel free to keep asking questions because I feel like students ask questions that I wouldn't have thought of, and it's feel like it's even educational for me even after doing this for all these years. So yeah, and Brian, when's the stretch coming?
What do you mean?
Don't you do the pre?
Yeah, it'll happen.
It's coming.
It'll happen.
Okay.
So
Famous.
there are a couple other people. There is our Zoom administrator. Marcia, can you turn on your video so everybody can see you? She won't be able to. Marcia Fay is on Zoom. You should thank her because she will be making sure that if you want to stay home or you're sick or you don't really feel like getting out of bed.
Marcia's the best. Thank you, Marcia.
You can still see the lecture.
She sent you the email with this
Yep.
with this Zoom link and is keeping track of everything.
We also have another admin. I guess I would call her admin. That would be Rebecca Thompson. She is the head of engagement and public outreach at Fermilab.
Engagement.
Did I say that?
Education and public.
Education and public outreach and public engagement. Thank you. We have tons of internship programs and other educational engagement things beyond this. You should talk with both her and Natalie if you want to do more stuff, and also me if you want to do internships, or us if you want to do internships. Other than that, that's most everything for ground rules. So now,
I will say real quick, I don't think we did the announcement, but both of you probably discovered that there are bathrooms at the back of the auditorium for those of you here in person, and if in the case of an emergency where we need to evacuate, we will tell you what to do, but basically there is a tornado shelter kind of like over behind here. Just in case anything comes up. Of course, in the event of a fire, we'd probably go out to the parking lot.
okay.
Also, for those of you who don't want to be embarrassed by your phone going off, just a reminder about it now. You're welcome.
Okay.
Any questions out there?
Oh yeah, that is a good question. Do
Just
you have
like
any questions?
overview stuff.
Anything you guys want to know before we get into the main program? What's
The
up?
main program.
What if you don't know anything about physics?
That was such a great question. Thank you.
It's all right, man. Cool.
That's the answer.
Yeah, you just come here to learn. Grab what you can. Maybe take some notes. Maybe go look up some stuff later. Also, ask a bunch of questions because that's how you learn.
You're absolutely welcome.
Yeah.
Those of you who were here earlier, Nate and I were talking. I mean, I didn't take my first physics class until senior year, so a lot of you are already ahead of me. And, you know, here I am, right? So it ended up being okay. So no worries. If there's something that you don't know, that's why you're here, right? I mean, if you already knew everything, there wouldn't be any point in coming. So we're here to be with you while you learn, and we're here to help you learn. And really, like you said, there are no stupid questions. There might be questions you feel awkward about asking, but that's okay.
So with that, unless there are any more questions, are there? You want this?
So we'll be taking questions sort of as the speaker allows. I think,
Okay.
Christina, you said that you invite some interruptions, so we'll be watching Zoom, and in person, we'll just wait for the mic before you ask your question, but like raise your hand or something.
And apparently I'm just learning. Remember I told you we're just starting this again. Now we have to run a safety announcement. We'll do that before.
Oh, okay.
So
Better
ahead,
than
Nick.
my half got things wrong safety announcement.
Okay. So I got to introduce you first. So we have pretty awesome physicists coming to the stage. Her name is Cristina Mantilla Suarez. You're from Ecuador.
Mm-hmm.
So she did her bachelor's at the Escuela Politécnica Nacional. She finished that in 2015. Then she went to John Hopkins University for a PhD in physics. She then became a Letterman Fellow here at Fermilab. So remember Leon Letterman that I showed you earlier? They made an entire fellowship in his honor that emphasizes teaching. It is a very prestigious fellowship. We have one of our Letterman Fellows here to give you a talk. And then finally, before we get started, before you start talking, I need everybody to stand up one more time. This is a Saturday morning tradition. So what we do, I know all of you have already gotten out of bed.
Also
You're already
Zoom.
here. I'm sorry?
Also on Zoom.
Oh, yes. Also on Zoom. Almost forgot. Everybody on Zoom, I need everybody on Zoom to stand up as well. And what we do to try to get into the space, to make sure that we are open for learning and absorbing, is we do a yoga breath exercise. I do some yoga. So we're going to take 3 deep breaths. Now stretch, get out the wigglies. Let's do the first one. Breath out. Oh yeah, that felt good, right? Got that science energy coming in. Yeah. The second one. Breath out. Yep, all that oxygen in your brain. Last one. Breath out.
Okay, can everybody hear me? Oh, yes, you can. Great, so my name is Christina, and I am from Ecuador in South America, and I came first to Fermilab in 2015. I was an intern for a year, and right now the job that I have is like kind of my dream job, so I'm like super excited to be here. I've never given a talk in this auditorium, so I'm like extra excited to be here. I think what I really want to convey to you today here on Zoom is what kind of science we do at Fermilab and why we do it, what kind of questions we're trying to answer, and what's basically next for the lab. Okay, sorry, we have heard logistics for like 15 minutes, but again, just a reminder, your job here as students is to just try to gather concepts that are interesting to you and you would like to learn more. In this lecture, I have so little time that I'm just gonna throw you concepts as much as I can. And then you can ask me questions, but also you can save some questions for like the remaining 10 weeks of this program. There will be many experts that will go much more in detail than what I will go on today on many of the topics that we will touch today. And then also the recording will be available, resources are online. And so I think especially if you're here in person, it's good to just interact, take some notes if you need to. Then you can go back and like, look at questions. Okay, then regarding the safety announcement of like turning off your cell phones, I'm gonna go back to that. So please turn it on. You can put them on silence. I will be using this interactive poll so that you can answer questions. So does anybody here do not have a phone? Okay. Great, so you all have phones, so you can take them out now and type in this link here. I'm sorry, my name is so long. The only option to like make it shorter is to like pay for it, and I just didn't want to pay, so you have to type in my whole name. It doesn't have an H, so it's just CR. And please type it also on Zoom. I think Marcia will be circulating this link also on Zoom. So just have it available for you. It should look something like this. So just waiting for some answers to come in. I'm gonna give you like 10 more seconds to do it. Sorry, can you? Yeah, there's a West guest Wi-Fi.
We'll have to register for the guest Wi-Fi, but it's pretty quick.
Don't worry, one minute.
Also, if we do have questions in person, please raise your hand and wait to be recognized, and one of us will come to you with a mic so that people on Zoom can hear the question as well.
Okay, can I get a show of hands of people that have finished and have successfully done the link? Okay, I'm gonna wait a few more minutes, seconds. Yeah, raise hand on Zoom, is that? Oh, okay, great. Thank you. Thanks for raising the hand on Zoom. Okay, I'm gonna move on. If you need to remember the link, it's my name and 824. So like you will for sure remember my name because it's on every slide. Okay, so let's just go back to this idea that Fermilab is a national laboratory. This is a map of all of the national laboratories in the US. I wonder if you recognize some of them. Does anybody recognize any names? Yes. Los Alamos. Did anybody see Oppenheimer recently? Oh, yes. Did you like it? Nice. Actually, my partner works in Sandia, which is very close to Los Alamos, so we went to see like a special like showing of the movie. And there's a lot of enthusiasm because you have like a whole movie that has been seen by many, many people directly related to your lab. So I'm actually pretty jealous. So yeah, so there are many labs by the Department of Energy. I think they're different and like their directions, and that's why you see them some in blue, some on red. Fermilab is right here in Illinois. If you didn't know, there's a second lab in Illinois that is called Argonne. It's like 30 minutes from here, pretty close, that also does very cool research. And all of these labs have like particular research directions that they want to follow. And some of them are very, very general. Like you can find within the same lab, like biophysicists or like people that do quantum computing or people that do research in nuclear physics. And some of them are actually much more specialized. And so Fermilab happens to be one of them. Okay, so now I have a second question to you, which is, what kind of science do you think is done at Fermilab? And so before you actually answer that to me, I'm going to just activate this poll. So now you can go back to this link and then just type in whatever words you think Fermilab, when you hear Fermilab, what kind of words come to your mind? And you can also do this on Zoom. Okay, so now we're going to see these responses. Sorry, there's a better way to show this. Okay, great. Okay, so physics is the main word. Accelerators, quantum acceleration, modern high energy physics, nuclear physics, combustion, that's an interesting one. Standard, perhaps on the standard model. Antimatter, that's a nice word. Astrophysics, mechanics, energy, research. Okay, great. These are all words that are like directly related to what Fermilab does. Some of them are. Okay. Sorry for people on Zoom. I was sharing this this idea word. Okay, so all of these words are actually really related to Fermilab. I will just tell you that both of them, particle physics, is perhaps one of the summary words of Fermilab. When you go to the Fermilab webpage, you will actually see this. And I think what is unique to Fermilab, and I want to emphasize this, is that when it was created, it was really oriented to like only do particle physics. And then it became clear that because many fields actually are very connected to particle physics, you needed to connect them all, and all of them are in some way done here in order to answer questions that particle physics is also trying to answer, right? So while you will hear a lot about particle physics, you will also hear about accelerator physics, like how do we build accelerators, why do we build accelerators? You will hear about quantum science, which is a new direction that the lab has been taking in the last 10 years. You will hear about cosmology, astrophysics, and then also how we build particle detectors, which is actually a direction that requires a lot more training, like technical training, than just theoretical. Okay, so before I really go into like what we do at Fermilab, I want to answer this first fundamental question of like how we do science or how to do science. And so I wanted to show this video from also a famous physicist. This person is Richard Feynman. Has anybody heard about them? Great, raise your hands. So he also won a Nobel Prize. He's a really famous physicist because he also had a really good way to teach things. When I was in university, I actually read a couple of his books. He was in Los Alamos as well. You may have recognized him in the Oppenheimer movie as well. And he had a couple of books of even relating his life as a physicist and what was interesting at that time. Great, but let's hear what.
Law. In general, we look for new law.
I'm just going to replay it.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply. And then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observations to see if it.
Okay, so what did he say? He said, first you take a guess, then you make a prediction, and then you compare that with experiment, right? So this like logical sequence always needs to be followed. Get out of here. Okay, so this logical sequence of like taking a guess, looking at predictions, and then also looking for a comparison with experiment is something that has been present in science since like the very beginning, right? And the more that we validate this method as well, we discover as well new laws, right? And so one thing that I want to do here is try to do an example of how we have built up some of the laws in physics, right? And so while we look for new physics, when we try to understand the world, we ask questions about how the world is working, right? And so one of the questions that we could ask is, how do we know that the Earth is rotating? Has anybody met a person who actually thinks that the Earth does not rotate? No. Okay, great. But I'm going to actually tell you today the evidence, if you ever encounter such a person, such that you can actually tell them why you think the Earth rotates. Okay, so let's take a guess that the Earth rotates counterclockwise, right? So at the same point, you will see Africa, but then later you will see Asia and Oceania. Okay, so the Earth rotates counterclockwise. Now we're going to try to do an experiment to prove this prediction. And so what we're going to do is we're going to put a pendulum in the top of the Earth. So this is in the North Pole. Has anybody seen pendulums? Yes. Where do you see a pendulum? Not quite yet. Yes, that's where I'm going. Where do you see pendulums in your real life? A clock. Okay, great. So a clock is like, yes? In a gym? I didn't know that. Okay, in the gym you also see a pendulum. Okay, great. And then you also see them in the Museum of Science, which I will come back later. But so when you see pendulums, usually they're like moving in one direction. A pendulum will go in equilibrium when it's in the center, right? So that means that if it's right in the center, it will just not move, right? And so when you distort it from the equilibrium, you put it in a different position because of gravity and because it has a pendulum that oscillates, it will do this kind of movement. And if there were no friction in the air, this movement will like completely keep going forever, right? The reason the pendulum is stopped is because we actually have friction in the air. Okay, so let's imagine we put this pendulum in the top of the Earth. We also give this pendulum some sort of direction, some sort of plane to move with. So like we determine in which plane it's moving, like which direction it's first going to the next one using this red arrow. And so, for example, a pendulum that is in a clock, it's always moving in the same plane, right? Which is determined by like the plane of the clock in the wall, for example. It's always in this direction. This pendulum could move anywhere if needed. Okay, so this pendulum is on top of the Earth, and now the Earth is again rotated. So again, you don't see Africa, you see Asia, but then the pendulum it still keeps rotating, right? And so this direction, this arrow here will indicate to you how the pendulum is moving. Now what happens is that because the Earth is rotating, right, you will actually see that the arrow is going to change, right? But you don't see that from like this point of view. From this point of view, the arrow is always going in this direction, right? So this observer's point of view is not very useful. What we're going to do is we're going to place a penguin in the North Pole, and the penguin is going to be able to see exactly from the point of view of the pendulum how the pendulum is moving. Okay, so now we're going to take the position of the penguin and imagine that we are the penguin themselves. And so the penguin kind of will be more on the Earth, right? So now we're looking at the Earth from the top, right? So this is again the North Pole in one of the stations of the Earth, and in the second image, the Earth has rotated. And so again, what happens is you still have the pendulum in the top. It's oscillating in one direction, and then again, when the Earth is rotating, the pendulum keeps oscillating, right? And so what you want to look for here is what is the direction of the red arrow? Like how is the pendulum oscillating or going back to its original position? Again, it's hard to tell unless you have a reference point. So we're going to place our penguin. The penguin is actually standing on Greenland, or I think it's Greenland, yes. And so originally it's standing on Greenland, and it will keep going on Greenland because the penguin will not move. But then what happens is that because the Earth rotates and the pendulum is placed on top of the Earth, instead of like having the pendulum always going in the direction of the penguin will actually see that the pendulum arrows will start rotating as well. So at the beginning, it will be going in the direction of the penguin. At some point, it will be perpendicular to the penguin. At some point, it will be in this direction. At some point, it will be like in the opposite direction of this graphic. And finally, it will go back to the penguin. And so this simple experiment of placing a pendulum on top of the Earth has already told you that if the pendulum moves, if the pendulum rotates, the Earth is also supposed to be rotating. And so just one extra piece of information is that while the Earth will rotate counterclockwise in this assumption that we've made here, the pendulum precession, by precession I just mean in which direction the red arrow will go, will be in the other direction, so clockwise. So in this case, it was going this way, and then you can tell that the arrow has been doing this direction as the arrow rotates. So this pendulum has a name. It's called the pendulum of Foucault. Foucault's pendulum, I guess. There's a book by Umberto Eco, who I recommend you to read as well, that tells a very interesting story about this. But can you tell me your name, sorry? Harper? As Harper pointed out, there's actually this pendulum in the Museum of Science of Industry. Has anybody seen it? Okay, great. Send us to the Museum of Science of Industry. So I'm going to just show a quick video again. It looks like this. It's a huge pendulum that is located in the top of a big ceiling. And as the pendulum keeps doing its oscillatory movement, you can barely tell because the Earth rotates once every 24 hours, right? So it's actually a very slow process. But these little slats that are placed over here are actually placed there in order for you to determine how the pendulum is moving. So as the pendulum keeps going and going and going, you can count how many slats have been actually turned over by the pendulum as it hits them. And so if you go back to the end of the video, this video is like 6 minutes long. You can tell that it's much closer to the slat, and then finally hits slat. But this took like 9 minutes, so it's actually very slow. You have to stay there for a while. Okay, so this is the Foucault's pendulum. It's a great experiment that happened in the 1800s. Okay, so now I want you to think a little bit more about this pendulum and think about also what happens in like other positions of the Earth. So we have said that in the South Pole, the pendulum will rotate, and this precession will happen in the time that the Earth rotates, which is 24 hours. So our next question, please don't answer to me yet. I'm going to activate it in the slides here. Is what will happen in the South Pole? So you have four options. First, same as in the North Pole, the pendulum will rotate counterclockwise. Clockwise. Messed that up. B, opposite as in the North Pole. C, no precession at all. And D, the pendulum does not work there. Okay, I'm gonna look. Great, so responses, opposites as in the North Pole, 73%. Great. Most of the people think about that. And then also, same as in the North Pole, a couple of responses. Thank you for not saying that the pendulum does not work there. Okay, so indeed, what happens is that the pendulum will do exactly the opposite as what's happening in the North Pole, right? And so what you will see is that if the pendulum is rotating in this direction, and if you completely invert the pendulum and take the pendulum arrows to like represent where is it going or like how the arrow is rotating, you will see that it's exactly the opposite as in the North Pole. Okay, now there's a much more trickier question. This actually involves some math if you really want to calculate how long it will take. But I'm going to ask this question of how long it will take the pendulum to complete a full rotation if it was not placed in one of the poles, but it was placed in a latitude in between, like for example, Chicago, which is in the northern hemisphere. So again, you have four types of answers. Okay, so go for it. So A is it will take more time than in the North Pole. B, less time than in the North Pole. C, exactly the same time as in the North Pole. Or D, it will not precess. It will just be 0 hours and 0 minutes. So people on Zoom are also answering. Okay. This one is a little more tricky. Okay, so here opinions are more divided. Most of them used to think that it will take longer than in the North Pole, but there seems to be equal opinions about whether it will take same as in the North Pole or shorter than. Okay, so let's examine this case a little closer. This thing is a little tricky to think because now you have to place your reference frame as somebody who's in Chicago as well, right? And then the arrow will still try to rotate. But it's a little harder to like think about like the full math depending on like the rotation of the Earth. But you can think of simply how the arrow will be going as the Earth rotates, right? So like if you have already assumed that, or you have already proven that the arrow will go in this direction in the South Pole, you can imagine the same thing from the position of the pendulum. And even though I'm not exactly showing the Earth rotating, you can just simply follow the arrow, right? So what the arrow will do is it will go little by little like this, right? And then finally in the opposite direction. And we don't see the opposite side of the Earth because I was a bit lazy to draw that. But eventually the arrow will come back to its own position, right? But because the Earth has the shape of like being simply round, right? And the radius of the Earth here will be much bigger than the radius that you will have to do in the North Pole. You will have to take more time than in the North Pole. So answer A is what counts here. that clear? Yes, okay. Okay, what about the equator? I'm from Ecuador, actually, so I will tell you what happens there, but you can tell me first. So again, let's just answer this question real quick. So go back to your phones. And, oh, sorry. Just go for it again. So answer A, again, it's same answer as before. How long it will take in the equator? Longer, shorter, same as in the North Pole, or 0 hours, 0 minutes? Dang. Okay, so most of you think it's longer than the North Pole. I think I misled you here because I thought I pointed that there was some direction between, or some relationship between the radius of the Earth and like how long it takes for the pendulum to rotate. But if you think about how the pendulum rotates, it's actually a bit more tricky than that. So the answer actually is D, 0 hours, 0 minutes, which 23% of you thought it was correct. So in the equator, the arrows will always be pointing in the same direction simply because the way of the pendulum is oriented, which is always in this direction, right? It's perpendicular to the edge of the Earth. Even if the Earth rotates, the pendulum will still be going in this direction, this direction, this direction. So there will be no precession at all. So if you actually put a pendulum in the actual equator, you will not see any rotation at all. And this is different from the case that we showed before, right, where the pendulum was located in a different latitude, because in this case, in this latitude, you still had some precession with respect to the North Pole, which is different from like just having to be in the exact middle of the Earth. If you go to my hometown, which is Ecuador, actually the capital Quito is located like 3 miles from the center of the Earth. So you can go to the center of the Earth, there's like a little monument, yada, yada. And there's also like a museum. It doesn't have a pendulum of Foucault, but it does have a couple of little experiments that are trying to relate to you this idea that if you're in the center of the Earth, you will not see effects that you will see in the northern or southern hemisphere. But I think actually all of these things that I'm showing in the museum might not be correct, but this particular experiment of the Foucault pendulum actually does tell you how to differentiate between the equator, northern hemisphere, and southern hemisphere. Okay, great. So this artifact has actually been with us for like many years. I think the first one was built in the 1850s, and it was placed in Paris. You can go on Wikipedia and see all the possible Foucault pendulums that you have ever built. And unfortunately, there's none in the equator, but there is one in Chicago. But just going back to this original idea that I want to introduce, all that has happened here is, again, the scientific method. So at some point, we have decided that the Earth rotates. We have taken a guess. And because of this guess, we have also inferred the consequences, right? We have inferred that the pendulum direction of the arrow will actually change over 24 hours. And this is determined by the laws of classical physics, gravity, and then just pendulum, oscillatory movement, etc. And so again, this distinction between taking a guess and predictions and calculations has happened. And then finally, what really has to happen is that we have to confront nature. We have to make an experiment and prove that this hypothesis is correct. If you don't, then all your laws are not sustainable, and you just go back to the drawing board. And so just 2 more notes that I want to say here is that maybe one of the reasons that science sometimes gets complicated is because your guess is either not obvious, right? So you don't know what the starting point is, or you have way too many guesses. It's going to take you forever to like actually prove which one is correct. And then also your experiments can be quite complicated, and you will see many of these examples of experiments that are quite complicated or results that are hard to interpret in the lectures that will follow this one. And more importantly, even if you have one experiment, this experiment needs to be robust enough that these results can be reproduced. You can place the Foucault pendulum in many, many places of the Earth and still see the same behavior that you predicted as depending on the location. And this is really what proves that the Earth rotates, right? Okay. So just going back to why we're here today, which is to explain what Fermilab does. I wanted to just place everything in the context of what are humans doing here on Earth and trying to understand what kind of processes are happening in nature, right? And this really depends on who you ask. Many scientists try to answer this question in like many different ways, right? If you're a biophysicist, or sorry, biology person, you go and try to study how animals behave, how many plants there are, what exactly determines the conditions of plants and animals in the Earth. If you're a chemist, you can try to go and study little by little chemical elements in like a lot of detail, and then also understand what kind of compositions, for example, have many things in the Earth as well. And we as physicists, we try to sustain this world under two big pillars, which are the laws of both quantum mechanics and then relativity. And these two pillars that actually sound like such hard subjects will actually be introduced to you in the next two lectures. So you will learn everything about quantum mechanics and special relativity and how these two big theories can actually create laws or sustain laws that can explain many of the things that we are wondering about the Earth. I will also say that even though I've emphasized the picture of the Earth here, we as physicists as well care in general about understanding the universe. And so hopefully many of you have already heard about this big picture of the Big Bang, where we have already theorized the origin of the universe via this theory that says that in the beginning, everything was super small, super compact, super dense, super hot. And then at some point it exploded. And in a very, very, very little time, in terms of like fractions of seconds, things developed. And then 13.7 billion years later, we are here as humans on the Earth with galaxies and stars and atoms surrounding us. And so this big picture that I tried to explain in the last 30 seconds actually took a really long time to understand, and we're still understanding. Even though we have plenty of evidence to tell this story, right, to kind of tell the story of like how the universe came to be what it is now, we also don't understand why. So like the simple question of like why this occurred is still an open question. And so one of the ways that we can use to answer questions about how the Big Bang happened is by actually looking at the universe out there. This is a picture that was recently on the news. Does anybody recognize it? Yes. The Hubble telescope? James Webb. Okay, great. So this is a picture that was in the James Webb telescope. It actually replaced the Hubble telescope. It's called Deep Field. This picture is, if you look at a tiny little fraction of the sky, perhaps like this, with a telescope from the Earth, you can actually picture all of this. And because we have improved so much on how we build telescopes and our precision to observe the universe, we can actually tell apart many things within this picture. In this picture, there's actually orders of magnitude of galaxies that can be identified. Some of these features that you see here are actually directly related to the structure of the mirrors that are placed within the telescope. And even though this picture is in reality just beautiful, it also tells us a lot about the composition of the universe, how stars evolve, how they form, and then even it can tell us about the age of the universe. And so bottom line, what I'm trying to say is that by looking at observations from astronomy and also measurements from cosmology, we can go back and try to answer this question of like exactly what happened in the Big Bang. And why was the structure formation of galaxies? What happened to go from like a very hot, dense state to actually have something like formation of planets or stars, which is really in the very, very late stages. But then what we also do is we also try to recreate the initial conditions of the universe. And so one of the ways that we do that is by trying to recreate this very, very hot, dense state with particle collisions. And so many of the things that we will also hear about here at Fermilab is colliders. There was that word already in the idea word. So you have heard about them. They're these big, big instruments. This, in particular, is the biggest experiment built by humans on Earth. It's a 27-kilometer ring. It's called LHC, Large Hadron Collider. It's essentially a ring that is underneath the border between Switzerland and France. The border is here in white. The ring here that is drawn is obviously underground, is like 100 meters below the ground. In each of these little points, what happens is that you take beams of protons that are actually as thin as your hair, right? Like even in a width that is as thin as your hair, you collect billions of protons, okay, not billions, sorry, lots of protons, and then collide them together many, many, many times within 1 second. So actually, we collide them every 25 nanoseconds, which is 1 to the 10 to the minus 9 seconds. And so what happens in these collisions is that these protons carry on and achieve velocities such as the speed of the energy. I will come back to you in a second. Achieve speeds very close to the speed of light, and then energies that are very, very, very high. And then when they collide, they try to reproduce exactly particles that were, or conditions as well, that were produced in the early universe. And by studying these particles, we can understand the fundamental constituents of matter. You had a question? So the question is, how do they collect the protons? The protons are coming from a bottle of hydrogen, simple as that. So hydrogen will have atoms. The bottle of hydrogen will have hydrogen atoms, which will have a proton and a neutron, and you extract the protons from there, and then you put them into one bunches. So actually, you have bunches of protons, which are like a little train of protons, and then going through the collider. Okay, I have to speed up now. Tell me about time. Okay, we'll have like a break in 5 minutes. Okay. Well, actually, we'll take a break much sooner than that. But I think there's 3 things that I want you to take away with you today about a very broad understanding of the universe. And if you have never heard about them before, they're actually very big concepts to understand. And each of them will carry behind them a series of these guesses, prediction, experiment series that have guided us to actually believe that this is true. And so the first thing I want to tell you is that the universe is very, very old. It's 13.7 billion years old. There's measurements of how old it is, and we have these measurements from cosmology and astronomy. A second, but still related to the universe thing that you need to learn is that the universe is expanding, and it's expanding like a loaf of bread, where everything, like when you like put it in the oven, everything like expands 1 point from the other. So it's not that it's expanding directly from us. Is that if you were to be in a different point of the galaxy, you will still see that the universe is expanding, even if you were in a different point. Exactly what happens as if you were in a loaf of bread. In the center, everything seems that it's expanding. In the outside, everything still seems that it's expanding or going away from you. And then even more intriguing is that this expansion of the universe is accelerating. So the more time it goes, the universe expansion is actually going faster than what we saw before. So this is a big concept. We'll talk about it later. Second concept, which you may have already heard about it in like your physics class, is that we as physicists study normal matter. Everything that makes this floor, everything that makes this clothes, everything that makes my human body is made out of atoms, and atoms are made out of elementary particles. And by elementary particles, I mean particles that literally cannot be divided and just be divided into different or smaller particles. And so these elementary particles, such as the electron, are there, and we study its properties by looking at these signals in our particle colliders. And then a third thing that I also want you to take away from this is that while we understand the universe, its composition as something that has a lot of normal matter, we also know, and are pretty absolutely sure, that there is something else, some other matter, that it is not the normal matter that we call dark matter, for a lack of a better term, and actually makes up the composition of 63% of the matter in our universe. So like most of the matter that exists in our universe is actually not understood at all. So the nature of dark matter is one of the big questions in particle physics. So what I'm going to do now is I'm going to go through why each of these questions happen, but I'm going to make a break because it's 10 o'clock, and so everybody can like stand up and just take a break from this lecture. And if you have any particular questions, just come talk to me, and we'll come back in like 10 minutes.
So hey everybody. Oh, sorry about that. You know what? Let's give it 15. So we'll be back. Is it 10 on the dot now? It's 10:02, so we'll be back by 10:17. Go take a walk. People on Zoom, go pet your dog and get a snack or something. I have a couple of announcements to make. There are 2 people who did not sign up. We need an Anna Matiovosoyan. I'm probably not pronouncing that correctly. Could you please come to the front? And Bala Natarajan, please come to the front. You're in the front. All right, yeah, come to the front, and we will work out what we're doing here. Other than that, yeah, go use the bathroom, walk around, get in the sun. Zoom folks will be back in a bit. If you have any questions, hang out, and we will answer them. Okay, everybody should be finding a seat. Welcome back. We expect you to sit next to each other, fill in the front. You guys know the drill. And now we're going to get at some Zoom questions before we get back to the regular lecture. Yep. So hopefully the Zoom people are back, because you guys got some pretty complicated questions, and we're going to try to get to them. So do what you can.
Welcome back, everyone. Welcome back, everyone.
Yeah, okay. Okay, okay, you all greeted me with questions in Zoom, so I just want to answer a couple of them that are kind of related to what we'll talk about in a minute. So I will just kind of pick up randomly. So very basic questions. Can elementary particles decay, like electrons decay? Actually, was answered, electrons can decay, as far as we know. Protons, actually, protons are super stable. We are looking for the decay of the proton, but we haven't found it. We haven't seen it decay at all. Can quarks decay? No, quarks cannot decay. We will talk a little. Oh, what is the difference between alpha and beta particles? Essentially, it's its composition. I forgot. What's beta?
Okay, so alpha particles usually decay. You see a helium atom. So it's typically, when I say helium atom, I mean it's a pair of neutrons and protons that decay together. They're typically very heavy, and that decides the sorts of radiation that you have to deal with. Beta decay is actually one of the things that produces neutrinos, inverse beta decay. Completely different process. It only involves electrons. It is a type of radiation, but how you deal with it is different. So they're just two different types of radiation, and how you have to deal with them are different. Beta is just an electron. I'm sorry, I didn't say that. We got an in-person. Okay, it's a follow-up. What you got?
What's a neutrino? A neutrino is an elementary particle. So you're kind of anticipating my very, very basic questions that I will talk to you about today. But a neutrino is an elementary particle. Is one of the very interesting particles that we study because it interacts very, very weakly. And it takes its name from people that thought it would look like a neutron, but it's not a neutron, so they say neutrino. And they're very, very light, and they interact very weakly. By interacting very weakly, I mean that it's very hard to see the sign of neutrinos passing by. Okay, I think many of the questions that were posted on Zoom, and then also the ones that I heard during the break, are actually anticipating a lot of what we will cover in the next 40 minutes. So I better get started. So I gave you these three basic concepts, and I told you no evidence for it, as if you were to just believe all of it. I think that's not very reasonable. So now I'm going to try to tell you why we know each of these three things. So I will start with the universe age and its expansion. Okay, so simple question. How do we know that the universe is expanding? A very basic answer is that we have studied light from extremely bright supernova. Supernova are actually an explosion of an star. In this case, is this point here outside of a galaxy. And what makes supernova super interesting is that they have a brightness that can be identified quite easily. So you can characterize the brightness of a supernova and sort of know what to expect when you see a supernova explosion. And the same thing happens for other objects in the sky that are called Cepheids, for which you can also measure its brightness. And so from this supernova, we have measured two things, and there was a question in the break directly related to what I'm about to say now, which is from supernova, you can actually measure the velocity of these objects. And so one way to measure velocity in astronomy measurements is by looking at some particular measurement that is called redshift. Redshift is talking a bit about how light changes its color as it's moving away from us. if you have heard, has anyone heard about the Doppler effect? Great, I see a lot of hands. The Doppler effect is something that happens as a source, like a wave, is moving away from us. So for example, when you hear a police car or an ambulance approaching or going away from you, you will note that the sound that it makes, it's very different from when it's very far away from you than it's when it's very close to you. And this is because the sound waves have shifted its wavelength or its frequency. The frequency and wavelength are inversely related to each other. And because this shift in frequency, you actually hear something different. The same thing happens with light. You will learn a lot more about how we know that light is a wave, but light is a wave. And so when light propagates and it propagates very far away from us, it will change its color depending on how far away it is, and also how big is its velocity. So the bigger its velocity, you will see a bigger redshift. And so a redshift just means that the color that you see will be going more towards the red. So if you see a star that is moving away from you, its light will become redder as its speed increases. So you can infer this property from a supernova, velocity, and you can also infer something else which is directly related to the brightness of the supernova. And what you can infer is the distance or time, or the distance of how far away is the supernova from you. And so here the analogy is, think about what happens when you see a motorcycle approaching to you very far away from you in the night. And so the light that is coming from that motorcycle is kind of like dimmer. As it comes away from, to you, as it comes to you, the light of this motorcycle is actually much brighter. And so you actually know what to expect just based, what to expect of the brightness just based on the distance. And so depending on how bright a supernova is, you can infer how far away it is. And because you know that everything moves at the speed of light, you can also infer from the distance, you can infer how long ago the supernova happened in light years. You can also infer the time of the supernova. And so essentially you have these two measurements, velocity and time. And what happened is that many people did actually very precise measurements. I'm just going to show a caricature here. It's not real data, where you were essentially plotting distance versus velocity. And so if everything was expanding at the same rate, you will see that the distance and velocity will always be a steady curve, right? So like basically what's happening in black here. And so it means that that everything is moving away from you, right? But the velocity is constant. There is no acceleration. You have learned about hopefully acceleration in your physics classes. But then what we actually see is that when we plot distance versus velocity, we see the red curve. So what happens is that everything is accelerating, and the farther away that things are from you, the faster that they're moving. And this is why the universe expanding concept is so interesting to like capture, because it's actually hard to imagine what happens. So that's the main piece of evidence of like how we know that the universe is expanding and this expansion is accelerating. I will mention that besides this elementary measurement of a supernova, there has been confirmation also from different objects that are called Cepheids of exactly measuring the rate at which the universe is expanding and expansion is accelerating. There was a recent Nobel Prize as well on like how to develop better a person to develop a better method to like measure this expansion rate. But even though the expansion rate of the universe has been measured, there's still controversy about exactly what is expansion rate and whether these measurements at all are conflicting. And this is, you can Google this Hubble rate a problem in physics now. Great, so that's like the first question I wanted to answer. I will come back about elementary particles in a minute, but I also wanted to tell you, how do we know that dark matter exists? So this is a question that I actually get to answer in my real seminars when I tell about the research that I'm doing right now on dark matter. And when I try to answer the question, there's actually many evidence that we present, and I don't have the time to do it today. So you will hear about all of the evidence in your cosmology lecture. But I will tell you at least one piece of evidence that we know that dark matter exists. Right, so one piece of evidence that we have is that we measure the rotation velocities of galaxies, of stars in galaxies. And what we observe is actually much different from what we expected. So we expected that the velocities of galaxies would follow this distribution with respect to distance. This distribution with respect to distance, right? Where stars that are closer to the galaxy would stars that are closer to the galaxy would move at a certain velocity, and then others that are farther away will move at a different velocity. And then what we actually see is the picture here on the right, where we see that the stars that are very close actually move at the same velocity that the stars that are very far away. This concept is actually kind of hard to grasp. So let me just go back to the beginning of how we know or why we care about measuring rotation velocities. And so I have a question for you just to think about a little, which is, in our solar system, just going back to what we know in our solar system of planets that are rotating around the sun, which planet do you think will rotate faster? So again, let's just think this is my last question, hopefully, from these activities. So let's just answer it real quick. Okay. So you expect that the planet that is closer to the sun, Mercury, will rotate faster than the planet that is very far away from the sun, like Neptune. This is just based, I guess, from intuition of how much pull we have from the sun to the planets, right? So if a planet is very close to the sun, it will have a bigger pull, right? So it will rotate much faster than the planet that is very far away from the sun. And so the same thing happens for the velocities of galaxies, right? So okay, this is just a plot kind of telling you, if you were to plot the speed that you expect from the distance of the sun, you will get kind of this plot, right? So the planet that is closest to the sun will have a larger speed than the planet that is farther away from the sun. I think by then we still thought that Pluto was a planet, and it has. But okay, so going back to the mystery of velocities of galaxies, what we saw is this different distribution, right? So we still plotted the rotational velocity in the y-axis versus the distance from the center of the galaxies for different stars. And what we expected, right, was what is happening here in red, that as stars are closer to the center, you will have a larger rotational velocity, and there's actually different laws. The picture that I presented here in this plot is only following gravitational laws. Here you have to take into account the shape of the galaxy, so it's a little more complicated. That's why you have this red shape here. But I think what I want to point out is that in general, you expected that as you go farther away from the center, very, very, very far away in light years, you will expect that the stars will be moving much slower, right? As you will expect, the distribution will go down. You will have lower velocities. But instead, what happened is that the measured velocities were actually kind of constant. So the stars that were farther away from the galaxy are moving almost as fast or even faster than the stars that are near the center of the galaxy. And so this it in itself was already a mystery in the 1930s. It was then later confirmed in the 1960s. And so what you can think of is that you can put this naive explanation that if you have a galaxy, right, that is made of stars and gas, and then you also have some gas in the galaxy, and you have some extra stars at the edge of the galaxy, you will observe that some of them will go at a given velocity, like 100 kilometers per second. I'm just inventing this. And then the ones at the edge, what you would observe as well is that they will also go at a large velocity, like 120 kilometers per second, like even faster sometimes than the ones that were close to the center. So this observation in itself was like a mystery. And a very broad explanation would be that there is something else, some other pull that is going around, and is basically going all around the universe. There is no focus point of this matter that is called the dark matter. So this matter, it is not similar to the stars, similar to the gas. It's not made out of anything that we know it exists. Like, it's not normal matter, but it is something that is exercising some sort of pull over the stars and gas in our universe. And it's surrounding everywhere. So that's why I kind of draw it as like something that is just out there in the universe. What it is, we don't know, and there's actually many explanations of what it could be. I will also say that many of the research that is done here at Fermilab is trying to explain whether dark matter could be a particle, for example, or could be something else that explains different cosmology measurements. There was a question of whether dark matter could be one of the particles that we know it exists now, but that question was quickly discarded by looking at each of the particles that we know exist now. I will come back to those in a second, and then seeing that each of the properties of the particles were not really consistent. First of all, dark matter should be very, very, very stable. Many of the particles, like for example, the Higgs boson, decay in like instants of a very fraction of a second. And dark matter must be stable in order to like hold the universe together for like 13.7 billion years old. So like dark matter should be stable. That kind of throws away many possibilities of particles. And then also, we have seen evidence for dark matter besides rotation of galaxies that confirm that dark matter actually has direct implication with the structure formation of our universe, how galaxies, how planets came to be together. And because of this evidence for structure formation that goes beyond the laws, that actually is directly related to the laws of general relativity, we also know that there is no such thing as, or it is very unlikely to have a modified theory of gravity that could explain the pull of something over, of an object over some heavier object. So while you may have heard that there's some, that gravity perhaps could be wrong, that we're understanding it wrong, it's actually very clear to many scientists that this is not such the case, that we have evidence that, that dark matter is real, and that whatever it is following the laws of special relativity, and a modified theory of gravity will not follow, general relativity, and a modified theory of gravity will not follow general relativity. You have a question. Why don't you ask it in the microphone over here?
So are we measuring or like analyzing the effects of dark matter using gravity right now, or is that just a modified?
So all the evidence that we have of dark matter right now is because of gravity, right? So all the evidence that we have from dark matter is from measuring galaxies colliding together, is from looking at rotational velocities of stars in galaxies, and all of that is coming basically from cosmology, astronomy measurements that are coming from gravity.
So even if we don't like, from like the general relativity perspective, we like kind of state that gravity doesn't exist, but we're kind of ignoring that and still like analyzing dark matter through lens, right?
So can you repeat that again?
So like in general relativity, it kind of states like from like the space-time continuum and everything, they say that it's just not like gravity doesn't exist, rather just the bending of the space-time. We're not considering that, we're just still like analyzing dark matter through like how, since we talked about the rotation of the galaxy and how since there's some added mass to the galaxies, it's causing the outside of the galaxies to spin at the same rate as the inside of the, like closer to the center as well, right?
Right. Okay. So this example, yeah, it's very close related to like perhaps how you would modify gravity to like account for that extra mass. But there's another example. Unfortunately, I didn't have time to do it in these slides here today. But there's an example where you have what is called a bullet cluster, which are like two galaxies colliding together. And in this collision of galaxies, what you see is an effect from general relativity that is called gravitational lensing, which is that when light passes through like a very, very heavy object, you see that the light gets modified, gets bent. And so because you see this light bending, you see evidence of like presence of some extra matter, that it is not gas, it is not stars, that it is present in the center of this collision, and it is not forming these two galaxies. And so because you have this gravitational lensing evidence, you know that dark matter actually follows the laws of general relativity. And so in that way, by having this extra evidence, you kind of discard that there should be some sort of modified gravity that should account for this extra missing mass. Okay, so that's dark matter. Dark matter is something, I don't know what it is, but it is out there, and we are looking for that. And so just going back again to my picture of like taking a guess, looking at what the prediction calculation should be, and then confronting nature. These two examples really show that we have done that, right? So we have taken a guess that the universe is expanding, taking a guess that there should be extra mass in our universe, and then looked back to the observations or calculations of whether you have velocity, given intensity from a supernova, or you have galaxies that are moving at a different speed, and then saying, okay, nature, what is the answer? What is exactly happening here? And it has told us, okay, the universe is expanding, dark matter exists. And I think that's what is so interesting about the scientific method, which is that it is just very robust, and it tells us with some confidence what how to do science. Okay, last question, which is that in these past situations, so like going back from the pendulum of Foucault to like these two examples that I have shown here, what do you think has happened? A, we have confirmed hypothesis. B, we have rejected hypothesis. C, neither, but theory is more robust. And D, science is a lie. Oh, let me just go back, sorry, before you can answer. The last activity, I promise. Okay, that's awesome. This is what I wanted to hear. So we have not either confirmed the hypothesis or rejected the hypothesis. What has really happened is that we have just made the theory more robust. And I think this is also one of the nice things about the scientific method is that essentially, we can just never confirm a hypothesis. We can only reject a hypothesis. We can only prove that something is not true by like looking at experiment results and then saying, okay, the experiment results actually reject my hypothesis. But even if the experiment results confirm your hypothesis, it does not tell that your hypothesis has been like truth and is universal for all, right? There's still many cases that you still have to cover. And the real reason that you have arrived to like laws of physics, like for example, special relativity or quantum mechanics, and we like look at them with like, you know, as the base of like many of our theories, is because many experiments have actually proven that these laws are correct, right? And so we assume that the laws are correct, but there could always be the case that they are not. And this is why we have to do experiments. Okay, and so I just have a final challenge for you, and this is really something that is going to be up to you over the next few lectures, which is that you will see a large number of experiments or situations being described to you in the next couple of weeks, whether it's in like your lecture of quantum mechanics or whether it's in your lecture of cosmology or like particle accelerators. And it is up to you to like see what in each of these situations identify what was the guess, what was the prediction, and then finally how did the experiment confirmed or rejected whatever you were guessing. Okay, I just want to end this lecture in the last 20 minutes by just going back to the fundamentals. I have one third point in the biggest slide that I ended before the break, which is talking a bit about elementary particles. And so I want to tell you a bit about what we know about elementary particles and what kind of science is Fermilab doing that is related to all of these three big statements that I did before. Right, so the first thing that I wanted to say, and hopefully you have heard about this in like physics class already, is that we know that normal matter, I am not talking about dark matter right now, is made out of atoms, which atoms have particles inside of them. They have electrons. Electrons are elementary particles. They cannot be divided. They cannot decay. And the electrons are surrounding and rotating around the nuclei. The nucleus is made out of protons and neutrons. And protons and neutrons are actually not elementary. They are composite. They are made out of even smaller particles that are quarks. Quarks are a funny name. Actually, they're like a yogurt in Germany. I don't know who came up with that name. But quarks are just particles that happen to be bounded to these protons and neutrons particles. And so even outside this picture, or like even going in more detail about this picture, about like thinking what is really making out the world, what is making out every possible thing of matter that we know of. When trying to answer this question, we have come up with this table, which we call the standard model of particle physics. And the standard model was actually one of the keywords in our key idea, slide a couple of slides ago. So the standard model of particle physics is essentially what you would think of as the chemical table, right? So you have seen the chemical table in chemistry. It's made out of all the possible elements that we have ever discovered, and then you go and memorize it. I used to like memorize it in like these little rows with each of these names, and then also these little rows, and I have forgotten most of them. But the same way that we memorize the chemical table, we memorize this table as particle physicists. And this table is just telling you which particles you have identified as being elementary. So I will start with the easy ones, which hopefully you can recognize. These little guys here are, each of the letters represent a particle. So E stands for electron, U and D represent the up and down quark. All of the quarks have funny names. It's up and down, charm, strange, top and bottom. So it's like kind of easy to remember. So electrons and quarks essentially constitute everything that we see in this room. So electrons and quarks are actually made up, quarks made up of the protons. So the proton is made out of 2 up quarks and 1 down quark. A neutron is made up of 1 up quark and 2 down quarks. Once you have made up protons and neutrons, and then you combine electrons, you have atoms, and atoms are essentially everything that makes all of the possible elements that are in our world. So essentially in this room. In this table, you also have these 2 colors, right? Violet and blue. So you have essentially quarks and leptons, and quarks are actually all of these, and leptons are all of these. I only mentioned like this first family here. Leptons are things like electrons, which you have heard of, but there's also 2 other leptons, the muon and then the tau. And then they only differ from each other, so basically going in this direction, they differ from each other on their mass. So a muon is like the heavy cousin of the electron, and the tau is like the uncle of the electron by being like so heavy. Okay, so those are leptons. They are related by symmetry, which are like these cousins, right? So like muons and electrons and taus are related by symmetry, and then quarks themselves, like up and down, charm, strange, and top and bottom, they have their own symmetries that they follow. Neutrinos, I got asked about neutrinos earlier. Neutrinos are these funny new particles. They all kind of have like some Greek names, or not all, but some of them. And so neutrinos, you can have neutrinos of different types of flavors. So like you have a neutrino that is electron flavor, muon flavor, or tau flavor. So that's why you have nu E, nu mu, and nu tau. So you have 3 types of neutrinos. Neutrinos are kind of interesting, and we heard a whole lecture about them because they interact so vividly with everything that we know. They're actually really, really hard to detect. At this point, you have tons of neutrinos passing through you from what we call cosmic rays. Cosmic rays are particles that are arriving at an atmosphere and then going through our atmosphere and creating tons of muons, and then the muons decay, and then you have muons passing through, and then you also have neutrinos passing through. And you cannot feel them because their energy are deposited, or they basically don't interact with your human body. Do you have a question? Oh, okay. Okay. So those are neutrinos. And then finally, this column here, this column perhaps is the most important of all because it's telling you about the particles that mediate interactions. I've been talking about interactions as if it was just something that was easy to understand, but interactions are really everything that is ruling out how one particle behaves when another particle is nearby, right? And so interactions are of different types. You may be familiar with some of them, like for example, the electromagnetic force. The electromagnetic force is mediated by one particular particle that is called the photon. The photon is light, and the photon mediates all the electromagnetic interactions. This one is a little more tricky. G stands for gluon. The gluon is what holds the quarks together in a proton and in a neutron. So this gluon is the particle that mediates the strong force, so it binds nuclei together. And then you also have the W and the C bosons. These W and C bosons are actually present in like radioactive decays. Like for example, the beta decay that Brian mentioned, when you produce neutrinos, Ws and Cs are always present. Ws and Cs actually decay very fast, as well as the Higgs, and therefore you usually don't see them in your usual life. Finally, we have the Higgs boson, which completes the standard model. It was discovered in 2012. So only 11 years ago now. And it is so interesting. You will hear about what exactly the Higgs boson is, but I will just tell you that one of the reasons that we were so excited about the discovery of the Higgs boson is that it is directly related to the mechanism that gives mass to elementary particles. It does not give mass to you, but it gives mass to the electron, it gives mass to the quarks, and therefore if the electron and the quarks have mass, you will have protons, you will have neutrons, you will have atoms, and you will have the universe as we know, and this is why the Higgs is so important. Okay, I will also tell you that our understanding of particles, this is just a bit of history because I kind of like hearing about history of physics, like how people came up with all of these possible particles. So I have listed here the discovery of particles as we know, and some of them are elementary and some of them not. This is why the list is so big. So perhaps the first particle that was discovered actually was the electron. I haven't even bothered to like putting it here. Well, we had some idea of the idea of atoms and nucleus with Rutherford's experiment in the early 1900s. Then you had positron, muon, pion and kaons. Has anyone heard about pions or kaons? Only Brian. Okay, doesn't count. Pions or kaons are like really interesting particles as well because they the way that they decay has been used many times to like test the precision of the standard model. You have lambda particle, I don't care about that one. Antiproton. Antiproton is essentially the proton, but is antimatter. I am not talking about antimatter here. You will hear about 3 lectures from now. But antimatter is essentially the same thing as matter, except that it has an opposite charge. So if the proton has positive charge, the antiproton has negative charge. It is not dangerous at all. It just happens to be way more matter than antimatter in our universe, and this is a huge mystery in our world right now. I wanted to talk about this one here, the upsilon. Brian mentioned it. It was discovered actually here at Fermilab by Leon Lederman because the upsilon is made out of 2 big quarks, and then it decays into a pair of muons, and it is a very simple experiment to do, and it was discovered by Leon Lederman, so that's kind of interesting. There's a funny history about the name of this upsilon. I think at some point in the first round of the experiment, they thought that they had already discovered the particle, so they kind of claimed it. Leon Lederman was like leading the experiment, and then like they decided that okay, that was not the particle. They just needed more data. They did more data. They discovered the particle, and then to this other particle that they thought had discovered first, they named it Oops Leon, as like Oops Leon Lederman, you screwed up. But at the end, the final particle was actually named Upsilon. Okay, that was already 1977. This is kind of getting close to our age right now. Finally, W and C bosons was a big discovery happening in the collider that was placed where CERN is at now in the 1980s. In 1995, there was a particle discovery that was announced in this very same room. It's called the top quark. It's the last quark that was discovered at Fermilab. And then finally, in 2012, the Higgs boson was discovered at CERN. And by discovery, the people that theorized it won the Nobel Prize, and the people that did the experiment as well. Okay, I just want to say that even though we have discovered many of these particles and we know that they exist now, we have followed up not only by discovering them, but also measuring the properties. The same way that you would measure properties about the chemical elements in the chemical table, you will measure properties of these particles. Like, for example, properties that we care about a lot are like the mass of the particle, the spin of the particle, and how it interacts with other particles. And there's a very precise measurement, for example, the magnetic moment of the electron, that we have measured this in like parts of a million. Parts in 10 to the 13, so it's actually more than a billion. Okay, I will also say that one of the very exciting things that happens at Fermilab is that we have particle detectors, which are instruments that allow us to actually see particles. Perhaps my favorite particle experiment to like show is something that's called a cloud chamber. It's actually, we have one of these in the Lederman Science Center, which is open to the public if you want to stop by at the end of your visit. And this cloud chamber is essentially creating some sort of condition that is made out of alcohol, condensation, etc., such that in this condition of condensed alcohol, you can actually see tracks happening, right? Do you see them? Each of these tracks represents a particle going through. These particles that are going through are either because a source, like a reactive source, is being present in this cloud chamber, or also because we constantly receive particles that are coming by through us through cosmic rays. When you see like there's some strikes that are actually much heavier than others, right? Like you see a lot more of white in this picture. Each of these bigger stripes actually represent a particle that is heavier than the very light stripes, which are very light particles. I think this is amazing. It just really tells us that there's a particle going through. It's like a visual sign of particles. Yes? This is in vacuum. You know, you can actually do this in a petri dish at home. So it's not like it's not vacuum. It's just air that is being condensated. It's alcohol that has created enough condensation. You know how you see like streaks of the path of airplanes in the sky? Like sometimes you see white in the sky like that. This is exactly what's happening. As particles go through, they're just leaving condensation in the air, which is just visible to you. Yes? You have more condensation?
Let's wait for the mic, guys. Unless the speaker can repeat. Sorry, I mean, unless the speaker who has a mic can repeat.
Oh, I see. The question is whether that we see dark lines being drawn. I think this is okay. So you see like a mist. You see like a mist in this thing, right? And so this mist is really all these alcohol particles condensating. And so I think this is just an effect of like how much condensation you have in each region. And so it's not really particles. But what you really see is the white. The white streaks represents some interaction of particles with the alcohol. And so what you're proving here is particles that are charged enough to interact with electrons in the alcohol and then create this condensation. Okay, this is a cloud chamber. You should see it. You should do it. There's ways to do it at home, and they're really fun. This was one of the first particle detectors. There's actually many more. You will see, I think, one today. Keep your eyes out for the bubble chamber. It's a chamber that actually has high pressure and uses this high pressure to like essentially draw the trajectory of particles. So the same way that you can draw these lines or interpret them as trajectory of particles, you can actually see and take a picture of them in the early 1980s to see how these particles would go. And bubble chambers are actually so cool that are still being used right now. Our understanding of particle detectors have actually evolved a lot. This is even an old picture of the CMS detector, which I work with. I'm always very proud that my initials, which are Cristina Mantilla Suarez, are the same name as CMS. CMS stands for the Compact Muon Solenoid Experiment, which is located at CERN. This experiment is huge. You can see the scale of a person with respect to the center of the experiment. The beam itself is like just a little tube that is right here on the center. You cannot even see it. And surrounding this beam, we place all of these huge experiments, lots of complicated machinery. Well, not that complicated, but all this machinery that is connected. It has both sensitive materials like silicon. Silicon is a particular chemical material that allows us to see the interactions between particles. Is very interesting in that way. But you also have tons of electronics, tons of cables. You see these blue stripes over here. They're actually cables that are taking this data that is coming out of particle interactions that are producing an analog signal, such as a pulse, and then taking this pulse and then going back into storing it into data. And so as a particle physicist, you do not only learn about interactions of particles, you also get to learn a lot about how to build detectors and how to take data and then finally how to analyze it. Okay, I'll also say something about the standard model. So I have presented to you a standard model as like an absolute thing, like the same thing as the chemical table. The chemistry table keeps being evolving. We have such a robust theory right now of like particles that we really think that we should have seen most of the standard model particles. However, there are also some unanswered questions that make us believe that perhaps we should discover new particles besides the ones that I have shown. One thing that I want to say is that right now, or so far, the standard model has been extremely successful, and every experiment that we have done in particle physics has really proven that really stands the test of experiments that are trying to prove it wrong. And so really what we're trying to answer is like, where does the standard model break, or how does it break? Is there some sort of particle that is not following what we think it's following? And then finally, is there any other particle that is not included in that table? And so I leave you kind of also with this slide, which is open questions in particle physics and cosmology. So I've told you these three statements that I think we're pretty sure about. These are things that we're not sure about. We don't know the answer to. So for example, what is the reason for having these three families of particles? Like, why do you have an electron, an alpha muon, and also tau? Is there a reason to have like a heavier version of particles? why do you have more matter than antimatter? So there's both presence of matter and antimatter in our universe, but matter actually happens to be much, much more present than antimatter. There's an antimatter factory at CERN, which you can go visit, but it's actually hard to produce and very expensive to produce. And for some reason that we don't understand, after the Big Bang, more matter survived than the antimatter. Other questions: what is the mass of the neutrinos? Do the neutrinos have mass? They happen to be very light, but we don't know exactly the mass of them. We don't know what dark matter is, as I've emphasized. We don't know if it's a particle, if it's a big object, if it's something that we will never be able to observe with our eyes. We don't know why is the universe expanding. We know, and this expansion is accelerating. We know that it is, but we don't know why. And also why the Big Bang happened, why everything came out from something very hot and dense to exploding. And then finally, we also don't know if there's any new forces, new interactions, new elementary particles that are happening in our world. And all of these questions are just out there, and people can be particle physicists and answer, people can be astrophysicists and try to answer, and people can be cosmologists and also try to answer them. Okay, I just have 2 more minutes, so I'll just very quickly flash through this, literally 2 more minutes, that I'll tell you a bit about Fermilab as a lab that is trying to answer these questions. So Fermilab actually has complex that accelerates particles. I work in one of the experiments. It's actually located here. This one says proton beam line, and it receives beam from the accelerator. The main part of the accelerator, this one here, actually was decommissioned. It was called the Tevatron, and it was used to discover the top quark. And the Tevatron actually is much smaller than the Large Hadron Collider. This is the one that is active, and this one was decommissioned. I work at the CMS experiment at CERN, which is the one that I've shown you before. It's huge. The scale of these experiments needs to be huge because you need to build huge detectors. It's basically like a very, very precise pixel camera that is trying to understand what kind of interactions are happening in these proton-proton collisions. And I will also tell you that at Fermilab, we have tons of experts that are analyzing the data of these current detectors. This is how a collision perhaps would look like. We actually draw how many particles come out of these collisions. There are tons of them that we need to kind of sort through and see what are interesting and what are not. And we also have tons of people. This is a colleague of mine, Irene, who actually go and build particle detectors. And they start as something as small as this. Here, the kind of the shiny part that you see is the silicon detector that I was talking about. We have people that participate in the discovery of the Higgs boson, which was in the news. You will see plots like this when you talk about the LHC in 3 weeks. And then we also have people that are participating in experiments that are looking for neutrinos. Like, for example, the next generation of neutrino experiments will take a beam from Fermilab and send it all the way to South Dakota, 800 miles away. And then we will detect that beam over there, which is a huge feat to do. Yes? There is no tunnel, actually. There is just this, and then you see the blue part? That's where they're doing the tunnel. The neutrinos just go through the Earth without the tunnel. I want to skip this.
Please wait for the mic, guys. We're trying to be respectful to people on Zoom.
Oh, sorry. The question was whether there was a tunnel over here, and there is no tunnel. Thanks for the reminder. Okay. We also have people that look and work on detecting neutrinos. Brian can tell you about that if you ask. And there is these amazing detectors that are being built that are, for example, in this case, filled with wires and argon in order to detect these interactions. We have experiments that look for very precise properties of the muon. I think you will be able to see this experiment. It's called G-2. If you have followed the science news, it has actually been in the science news for the last 3 years because it has an anomaly, what we call something that we didn't expect to see. The value that it's measuring is far away from the theory, and we don't know whether the theory is correct, actually. So there's a lot of discussion happening here. You will learn about this. And finally, we have a lot of people that are working on experiments underground or very, very sensitive experiments that are looking for the presence of dark matter. Nate is an expert on that, so he can tell you about that. And while developing these detectors for dark matter, there's also people that are doing things like merging fields, like using laws that you know from condensed matter, how material should behave. to try to build detectors that are better for identifying particles. So for example, people have built detectors using germanium, people have built detectors using semiconductors, and now people are also building detectors using qubits, which is like this huge new idea that is coming out. And then finally, last slide, I also want to tell you that there's also people at Fermilab who are not directly particle physicists. There are people that have specialized themselves into looking at cosmology and astrophysics data and use this cosmology and astrophysics data to answer questions that particle physics care about. So there's people working in the South Pole with observatories. There's people working on the cameras that go inside the observatories to like develop better detectors. Okay, so that concludes my lecture. I think that I have taught you nothing in this lecture, but I just wanted to give you a flavor of what kind of questions we are trying to answer and what will you be able to learn over the next 10 weeks. And so for all of the questions that you have asked, sorry, I've repeated and have a typo over there, there will be answers in much more detail, but feel free to ask any questions now. I will tell you that I will be very excited about these next two lectures that you have, relativity and quantum mechanics, which will tell you about the pillars of laws that we have, from which we have built all of the theories that explain all of the physics that you will learn later. And then finally, I say that I think one of the things that I really like about Fermilab is this community. You have not only particle physicists that have been trained as physicists, you have engineers, you have accelerator physicists, you have people that help in different aspects of experiments, you have theorists that actually help out build theories for you to test. And so it's an amazing, amazing place to work. So yeah, so that concludes my lecture. Thank you.
Okay, folks. So we are running into a time crunch. Because we have not paid a ton of attention to the people at Zoom, we should probably take a couple of questions from Zoom, and then you will have, some of us will be on the bus with you for the driving tour, so you can ask more questions then. So do we have any particularly interesting questions from Zoom we want to get through?
Should I select them or?
Yeah, select them. You'll be answering them.
Okay.
Nate and I have been doing what we can to answer the questions over Zoom when we can.
Can you tell us if she picks one that's already been answered?
I will. So she should pick what she finds interesting, and I'll let you know if we already got it.
Yep.
Okay, this is an interesting one. So what is the difference between, Akshara is asking, what is the difference between dark matter that is described being right now and dark matter that we know of? I think one of the fundamental reasons that I didn't say is that dark matter is kind of similar to neutrinos. It like barely interacts, or like it does not interact as far as we know with light. It does not interact as far as we know via the strong force or via the electroweak force. And so all of the interactions that we have built up from like the ground up, right? Like all of these three fundamental interactions are just not something that dark matter seems to be interacting with. It interacts with gravity, which actually happens to not be part of the standard model, which is also an open question. But because dark matter doesn't interact via these normal interactions, it differs from matter as we know. We initially thought that perhaps neutrinos could be dark matter, but then neutrinos actually have mass and they're very light, and they also don't explain like the structure formation of the universe. Nate asked a question that dark matter is not in the standard model of particle physics. Which, yeah, I see like a big picture. Okay.
Yeah, the question came during your standard model slide of quarks, leptons, and bosons. So yeah, dark matter isn't in that picture, I guess. I don't know why I put the question mark.
It's not part of our picture. Yeah. Okay. I think that there was a lot of messages about names.
Do we have any quick ones from the poll, Nate, that weren't covered? I know that you really tried to get on top of those.
Well, let's see. I mean, one was just about particle annihilation. But basically, what I guess the question keeps coming up. When during particle annihilation, do the particles transform completely into pure energy? Or, you know, or what happens to that created energy if it happens in outer space in like a vacuum?
No, I think the way that I would think about it is that all the processes that we know of particles, like for example, an electron converting into 2 photons, are following energy conservation principles, or like whenever you have a particle annihilation, you will actually have that energy going somewhere else. And so I think that's like one basic principle that we follow. So when we see a physics process happen, right, like photons or electrons interacting, annihilating, whatever, we always look at what is the energy in the initial state and the final state, and energy must be conserved.
There are particles carrying that energy.
That's right. That's right.
Yeah.
The energy is always carried by particles. Yeah.
One other question. Well, I guess talk about life at Fermilab. One question was, is there any research here that helps with mechanical engineering, or maybe just talking about engineering support in general at the lab?
I think
and the role of
engineering is like a huge part of Fermilab, right? So you have mechanical engineers can help a lot on the construction of experiments, or like I have told you about these huge structures that are being built to like build the colliders, or like build particle detectors that are huge, or like in the accelerator itself, you need tons of mechanical engineers, right? So mechanical engineers is needed. Electronic engineering is also needed to like understand all electronics that are passing through. And so there's actually tons of engineers working at Fermilab. Yes.
So as last time I checked, these numbers might be out of date. There are 3,000 people working at Fermilab. 1,000 of those folks are physicists with PhDs. I think 1,000 of those are engineers, techs, and support staff, and the other 1,000 I think is maybe not 1,000. But I think about a third of it is probably like business admin, and I think the numbers break down. Don't quote me on that.
I'll second the engineering being a huge part of what happens. And I talk about this a little bit in my talk later on about how we build and how we produce and detect particles. But I will just say that when you drove up to Wilson Hall, this iconic building that we're in right now, those of you who did drive this morning, those of you who did not, if you see a picture of Wilson Hall, right next to it is a new engineering building that's just being built, and that's entirely based upon, that's focused upon engineering because it's such an important part of what we do to make the science happen. It's a really important part.
I think that there might not be any aerospace engineering jobs. That might be a little
Most of what Fermilab does, or it's a DOE, Department of Energy funded lab, most of it doesn't involve outer space. That's more of a NASA thing.
Mm-hmm.
There are some, I work on a CubeSat project, work with aerospace engineers at UIUC, so I don't think there's any on staff per se. It's mostly mechanical engineering support, electrical engineering support, but some of that goes into aerospace as well, more specific and not towards building.
Okay. Any burning questions you would like to ask? How about in the back? Oh, hold on, sorry.
Who was it?
What's the name of the experiment that was gonna put neutrinos between this lab and another one?
Dune. It's like the movie Dune, or like the books. Have you heard the books? Yeah.
It stands for Deep Underground Neutrino Experiment. There are multiple experiments that do that. We currently have one called NOVA that is running, and then we also have the Short Baseline Neutrino Program, which you will learn all about in the neutrino talks.
Other questions? Right behind you.
I was wondering, what is going back a couple slides, what was the property of general relativity that observed that light is bent near extremely strong gravity sources, like black holes? What was that property called?
Gravitational lensing. you can look it up and like see actually really cool images of like how we have seen that light is being bent in like actually observations. But you will learn about it, I hope, in the general relativity class as well, and like why exactly it happens.
Okay, thank you.
More student questions. Parents have to sit on their hands this time. But you can come up afterwards. That's fine. Students? Any more over Zoom? Any more in person? This is an amazing opportunity. But you can think of them later.
All right,
Paul?
all right, folks. With that, let's give Christina another hand. Okay, people on Zoom, I think Marcia will be setting up the virtual tour for you guys. So we will be waving goodbye. Please come in person. You'll get to see more things. For the people who are in person, we're going to go take a 5-minute break, and then we're going to get on the buses for the driving tour.
Okay, we will start our tour driving through the main entrance of Fermilab under Broken Symmetry, which is a sculpture designed by our first director, Dr. Robert Wilson, who had a vision for the laboratory that still shapes what we do here. The sculpture is made with remnants of steel from a decommissioned naval aircraft carrier called the USS Princeton. It weighs 42,000 pounds or 21 tons and rises 50 feet above the road at its apex. Ahead are some of the buildings in our neutrino research area, which we will be visiting later. As you heard, Fermilab was founded in 1967 and is a 6,800 acre or 10 square mile campus. Our site contains most of the major Midwest ecosystems, and in 1989, it was designated as a National Environmental Research Park, one of only 6 across the country. About 1/6 of the site is a restored tall grass prairie. We are driving through a portion of that prairie now. Now, the next building we will pass on our right, the low building there, is the Letterman Science Center, or the LSC. It was named for Leon Letterman, the person you heard about earlier, Fermilab's second director, who was a big proponent of education and engagement with the public. He's the one who brought the idea of Saturday Morning Physics to Fermilab in the early 1980s and helped to establish it. The LSC houses many of our physical and life science programs. It has hands-on exhibits, a science lab, a makerspace, and a gift shop. You may have noticed that the road has been curving since we entered and continues to curve through this wooded area. Dr. Wilson's vision for the laboratory was not only for scientific excellence, but also for stewardship of the land, aesthetic beauty of the campus, fiscal responsibility, and equal opportunity. Because of his passion for the environment, he directed the original wooded areas on site be preserved as much as possible. The ponds we are approaching on the right are used to dissipate the heat generated by the powerful electromagnets used to steer and focus the particle beams in our accelerator complex. They also attract a variety of the waterfowl that live and migrate to this area. Beyond the pond is the building you're sitting in, Wilson Hall. Now, as we make the turn toward the hall, you will see Aqua alla Funi, a sculpture that Dr. Wilson presented as his parting gift to the laboratory. Wilson Hall, our central building on site, is 16 stories and contains offices, labs, remote experiment control centers, an art gallery, meeting spaces, and a cafeteria. It is attached to the room to the room that our in-person folks were sitting in, Ramsey Auditorium. And Ramsey Auditorium seats more than 800 people. You may notice that you could see through from one side of the building to the other. Most of the office spaces in the building are on either the left or right side, and there are higher floors with crossover points. The central part of the building is an open, airy space called the atrium, which actually goes from the first floor all the way up to the 16th floor. Taking a look inside Wilson Hall, this footage was recorded by our creative services team, and we'll see more of the work later on in the tour. Now, to the right, you'll see one of the newest buildings, the Integrated Engineering Research Center. Now, the reason you're seeing the blue is at the time this movie was made in 2019, it was still under construction. But this building was actually completed in 2022, and it connects directly to Wilson Hall. It provides a space under one roof for our engineering specialists to work more closely with each other and with the personnel who work in Wilson Hall. The flagpoles on your right actually do fly the flags of the countries that participate in experiments based at Fermilab. Currently, more than 40 countries are working with the laboratory. As we swing around to the west side of Wilson Hall, you'll be able to see a squarish building on the left. That houses the first stage of our accelerator chain, where the particles for our beam are extracted from a canister of hydrogen gas. Our linear accelerator, or LINAC, is the second stage of the acceleration process. The LINAC is 500 feet long and extends from the squarish building beneath the rounded earth mound or berm that you're seeing. Particles reach about 70% of the speed of light. Their energy is 400 million electron volts when they reach the end of the LINAC. An electron volt is the unit that physicists use to describe the energy of a particle. At the end of the LINAC, the particles are transferred into the circular booster accelerator. The steam coming from the center of the booster ring comes from the water treatment plant that provides deionized cooling water for magnets in the accelerators. In the booster ring, particles are accelerated to 8 billion electron volts. As the particles leave the booster ring, they are traveling over 98% the speed of light. To give you a better perspective, we'll soon be looking at the same area from above. You can see the earth mound or berm coming right up to the roof of the linear accelerator office space. The accelerator itself is below the grassy area. At the end of the LINAC, we can see the booster ring more clearly. Across from the booster accelerator is the muon complex. The first building we are seeing will house an experiment called Mu2E, which is currently under construction. The goal of the experiment is to learn whether the fundamental subatomic particles called muons can spontaneously convert into electrons. The building next to it houses the muon G2 experiment. The experiment's muon storage ring is a 50-foot in diameter precision superconducting magnet. Physicists use the magnet to measure the spin property of muons, which they believe could reveal new physics. We'll be continuing the drive toward the biggest accelerator ring on the site, which is 4 miles in circumference. This is where both the main ring and the famous Fermilab Tevatron were located. The main ring was originally the highest energy accelerator on site. It was superseded by the Tevatron, the world's first superconducting accelerator, in the early 1980s. They are both located approximately 30 feet below the earth berm. Pipes that run above the berm cover the accelerator tunnel. The pipes contain cooling water to remove the heat generated by the magnets in the tunnel. Inside the main ring is the first prairie restoration site of the laboratory, which Dr. Robert Betts of Northeastern Illinois University helped to establish and maintain. The new construction site is for our big new accelerator project known as PIP2, or the Proton Improvement Plan. PIP2 will replace the existing LINAC and be the foremost facility in the world for particle physics research using intense beams. Protons from a hydrogen source will be formed into a beam and accelerated by superconducting radio frequency cavities built at Fermilab. Particles will go from 7% of the speed of light to 84% of the speed of light when they exit into the booster ring. When the new accelerator turns on in 2028, beam power will be 1.2 megawatts. A later upgrade will bring it to 2.4 megawatts. PIP2 is being built with significant international participation, making it a first-of-its-kind collaboration on accelerator technology for the Department of Energy. This new accelerator will enable the production of an extremely intense neutrino beam, an essential component of the flagship Deep Underground Neutrino Project, also known as DUNE. You will hear more about this when we drive past the DUNE on-site experiment area. The white building on the left is the Feynman Computer Center, which will be described a little bit more later. The big orange tanks were once filled with helium gas. Yeah, I see they're going pretty quickly here. The big orange tanks were once filled with helium gas that were later liquefied on site and then used to cool the superconducting magnets in the Tevatron. We are approaching the Illinois Accelerator Research Center, or IARC. At this facility, scientists and engineers work side by side with industrial partners to research and develop breakthroughs in accelerator science and technology and translate them into publicly available products and services. Fermilab was awarded LEED Gold certification for the design of the building. When Fermilab was built, the first accelerator in the tunnel was called the main ring, and it was the most powerful accelerator in the world. Its designed energy was 200 billion electron volts, but it eventually accelerated particles to 500 billion electron volts. By 1985, the Tevatron had replaced the main ring as the most powerful accelerator on site. The Tevatron was named after its designed energy of 1 trillion electron volts. It directed the beam using superconducting magnets. Protons circled the ring clockwise and antiprotons circled the ring counterclockwise. The two beams collided in the centers of the CDF and D0 experiments. The crowning achievement for both experiments was the 1995 discovery of the top quark, one of the fundamental particles of nature. Now it looks like we have driven halfway around the ring to the site of the D0 assembly building. Should be coming up here, which is the home of the D0 experiment. Inside this building, a 4-story detector captured data from the collisions of the proton and antiproton beams. 10 petabytes of data were collected over a span of 26 years by this experiment and are housed in the Feynman Computing Center, which you got a glimpse of earlier. In 1973, Fermilab began the process of restoring Prairie to the site. The main ring contains the oldest section of restored Prairie. Now let's see, we'll let the driving tour advance a little bit. The smoke that you see is from a prescribed prairie burn. Burning is necessary to maintain the health of the Fermilab prairie. It distributes nutrients back into the soil, removes dead brush, and kills invasive species. Fermilab's resident ecologists, our roads and grounds crew, and on-site fire department supervise all of the prescribed burns. The red barn we are passing is one that is original to the Fermilab site. So we have now completed circling the 4-mile main ring Tevatron accelerators, and we're going to be driving past the booster ring and muon experiments toward our neutrino experiment areas. First, we will pass by the old antiproton source, where antiprotons were created from proton collisions with a target. The collection and storage rings are underground and have been repurposed to provide our 2 muon experiments with an intense muon beam. We are approaching M18, a building in the main injector area. The main injector was commissioned in 1999 and is the largest, most powerful accelerator currently running on site. The building is elliptical in shape and approximately 2 miles around. It was formerly an injector accelerator for the Tevatron. Now its beam is used to create neutrinos for experiments both on and off site. Coming up on our right is a building for our short baseline neutrino experiments. One of the properties also on our right will be the site of a detector for the International Dune experiment. The new PIP2 accelerator will help create an intense neutrino beam. The beam will pass through an underground detector that will be located in the area of this spot. The beam will travel 800 miles directly through the Earth to the enormous Dune detector in Lead, South Dakota. The detector will hold approximately 70,000 tons of ultra-pure liquid argon and will be located about 1 mile underground in an abandoned gold mine. Physicists will use data from this experiment to shed light on some of the mysteries of the universe, such as what is the relationship between matter and forces? How do galaxies form? And how does matter exist? As you can see, the prairie burn is still going strong. Fermilab is hosting 3 neutrino experiments that will make use of a shorter beam line of neutrinos than the Dune experiment that I just told you about. This shorter beam will pass through 3 detectors sequentially. The 3 detectors are needed to study neutrinos at different distances from the target where the neutrino beam is produced. So we're going to be coming up now to these buildings. The building you see is the one closest to the target. It is called a short baseline neutrino near detector. The detector itself is underground, and the silver shed protects some of the supporting equipment from the elements. The next building that you're going to see is the liquid argon test facility. The second detector in the short baseline is located here, and the experiment, which is underground, is called microboon. The third detector is called Icarus, and it is the short baseline in the silver gray building behind this hill. The 3 detectors will help determine whether a strange particle called the sterile neutrino exists. The building to the left of this gray one is called the Minos building, and it is the on-site access point for the NOVA experiment, which uses a neutrino beam sent from Fermilab 500 miles north to Minnesota. The Minos building provides access to several underground experiments. We are now going to continue our tour heading east from Wilson Hall toward the IARC building. That burn is still going full swing. The Feynman Computing Center houses part of our vast amount of experimental data from CDF, D0, and other experiments. There's that computing center. The data is stored on magnetic tapes that are accessed robotically. We have the capacity to store more than 600 petabytes worth of data on site. We're approaching the IARC building. So there's the acronym IARC. And that orange building on the right was part of the CDF experiment. This area is called the Industrial Building Complex. Here we build and test equipment such as magnets and radio frequency cavities that are used in accelerator areas on-site and off-site. It is also the site for some of Fermilab's quantum research. The sculpture ahead was erected during Dr. Wilson's tenure and is called Trectricious. It is made from leftover cooling pipes used in producing the superconducting magnets of the Tevatron. Many of Fermilab's sculptures are made from recycled remnants of projects that were built on site. We're going to be heading now toward Fermilab Village. And we're going to be passing the bison pasture, and there's that red barn that you saw earlier that's on the left. You can see some of the large amounts of open land areas at Fermilab. Some of the land is leased by local farmers, and some is used for environmental studies. The area we are passing now shows some of the leased land on our left, and to the right, studies on switchgrass, a type of tall prairie grass, have been conducted. Now here is Fermilab Village. Before the laboratory was built, this site was owned by farmers and contained the town of Weston. The White Houses belonged to some of the original farmers on the site and were relocated to this spot when Fermilab was built. On the right, where the town of Weston was located, the area now has facilities such as guest dormitories and daycare for staff children. In 1969, Dr. Wilson, who was originally from Wyoming, purchased a few bison for the laboratory to help fulfill his goal of restoring the original ecosystem of the area. Fermilab maintains a small herd of bison and auctions the yearlings to keep the herd self-sustaining. We're going to be passing by that bison pasture again, and we will be stopping briefly so you could see some of the bison eating. Yeah, I have to say the bison are so popular that last year a bison cam was actually set up so people could just kind of take random looks and see what the heck the bison are up to. So now you see a barn here, but the bison don't normally use it because they actually prefer to be outdoors, even in the really cold weather. Oh, there they are. Yeah, if I'm not mistaken, 20-some babies were born this year. So they keep pretty busy. We're going to be continuing on to the original experimental area of Fermilab. The area that we're going to be approaching is called the fixed target area because the particle beams collided with fixed targets. We will visit all three sections of the fixed target area. The building on our right is called the Proton Pagoda. It once housed the control room for the proton area experiments. The proton area is the easternmost section of the fixed target area. You may notice that staircase in the building is in the shape of a double helix. We are driving between two beam lines in the fixed target area. You can see a berm to the left and another to the right. The berm on the left leads to the westernmost target area called the meson lab. The one to the right leads to the central target area, which was our neutrino area. A beam of particles travels through pipes embedded below the berms. You may have noticed our unusually shaped power lines. They were designed by Dr. Wilson to resemble the shape of the Greek letter pi. They were originally made of wood, but after 40 years were replaced with the steel version. The building with the curved roof housed experiments and was repurposed into the Fermilab test beam facility. Researchers from around the world come here to test detector components. We're going to be heading now to the central target area, formerly called the neutrino area, but now referred to as SIDET, short for Silicon Detector Facility. Okay. We are currently behind the SIDET, and we're going to be looking again at a marvelous old piece of equipment. It's coming up. It's a big bubble. There it is. It's a bubble chamber detector that was originally housed in that silver building behind it. It was the main detector on the neutrino beam line and was filled with liquid hydrogen. In the buildings surrounding the bubble chamber, there are clean rooms and labs for developing silicon-based components for detectors and telescopes. Ahead is the FAST, F-A-S-T facility, which stands for Fermilab Accelerator Science and Technology Facility. It is the home of IOTA, a small innovative accelerator used for testing accelerator design concepts. To our left, in front of SIDET, you will see a domed building that houses a high-ceilinged assembly area. It is used for the assembly of telescope equipment, such as DCAM, the imaging device for the dark energy survey. We are driving behind the meson area toward the test beam facility. Now, one last site we're going to see is the home of the Fermilab Fire Department. We employ a large team of firefighters who work in shifts. Much of their work is preventative. However, we are glad to have them on the site. For example, today they're out monitoring that prairie burn that you've been seeing. There's the fire department. So we're going to be ending today's tour by heading back to Wilson Hall. We hope that you enjoyed the tour. If you have any questions, please feel free to send me an email or check out the Fermilab website at fnal.gov. We also have a presence on many social media platforms, including X, of course, formerly known as Twitter, Facebook, and YouTube. So thanks again, everyone, for attending the tour and for being a part of the first class in the Saturday Morning Physics program. Like I said, if you have any questions about what I was narrating, if I can't answer the question for you, I'll be sure to get you an answer from one of our physicists, such as Brian, Cindy, or Nate. So I'll be sending out a link to the survey, and I hope that you participate in the survey and come back next week. So thanks so much, everyone, and take care. And oh, one other thing, the video from today's lecture, check the online schedule for the classes. A link will be attached to the lecture, and check back about Wednesday or so. We're going to try a new way to link the lectures also on YouTube. So between the editing and passing the information on to other folks in the lab, I anticipate that the link will be ready Wednesday or so. So thanks so much, everyone, and we'll see you next week.